Good morning, good afternoon, good evening, whenever you may be. Welcome to another exciting episode of ACE, 8th grade science, live from the Runnabucker, somewhere in the quarantine zone of the Southeast United States. Hope you guys are staying safe out there. Remember, as you watch these, go down in the comment section, say hi in the comment section. That's your attendance for the day. Remember to like the channel, like the video, and subscribe to the channel. Make sure you're kept up to date with all the new videos that get put out, and so you know exactly where to go find all your stuff from day to day. All right, so we're gonna get started here. So yesterday we talked about upwellings. So now one of the things that upwellings produce so much of the world's fisheries and marine biodiversity and everything. But then you think about it, it's like, okay, so now you got all that stuff there, but how does it actually live? And so, because outside of the water, here on land, us beings that operate on land, we have lungs to get our oxygen in and our carbon dioxide out, so our cells can do cellular respiration, and we can produce our energy at the cellular level and survive. So then the question is, how do fish do that? Because they don't have air to breathe, but actually, yes, they do. The reason they have air to breathe is they have dissolved gases in the oceans. So 8.E.1 hydrosphere. So we're talking about dissolved gases in the oceans. So today's lesson is going to be a little quicker. There's a lot of video and stuff to show with this, just because it's more of a concept than something we can demonstrate. But you just got to get through the fact that yes, seawater, water, a liquid can contain something that is a gas and still in a gaseous state. So I can explain how seawater contains dissolved gases. So we know that land-based organisms use oxygen from the air to perform cellular respiration. Plants use the CO2 given off by animals to perform photosynthesis, which produces oxygen as a byproduct. The organisms that live in the ocean need the same gas exchange to support their own lives. Fish have gills to perform this gas exchange process that our lungs do for us. Gills exchange carbon dioxide for oxygen in the water. But now here's the question: how do those molecules of gas get into the water? So seawater has many of the same gases dissolved into it that exist in our atmosphere. Remember, in 7th grade, we were talking about air pressure. Just a refresher, but air pressure is essentially the weight of all the gas. I know that doesn't want GA. Weight of all the gas molecules in the atmosphere above the point of measure. So the air pressure, pushes down on the air molecules and on the bottom. And so when you're over a body of water, the bottom of that column of air is touching the surface of the water. So there are molecules continually bouncing and being pressed into the surface of the water. So the surface of the water is not usually calm and glass flat. It's just being agitated by wind and waves. So you've got water coming up and crashing down like that. And so then you have these gas molecules being pressed into it by air pressure. And so what ends up happening is air pressure pushes the molecules of gas into the water, and they're captured by the agitated surface. This is a very basic explanation, but effectively it's what we need to remember, is that those gas molecules get pressed and get captured into the surface water, and then eventually they get dissolved into the water. I have a large fish tank at home. And one of the things you have to do if you have a fish tank is you have to remember to have water stirring. The surface of the water has to be kind of ripply. You can't have nothing. You can't have just a glass top surface of water on your fish tank. Otherwise, there won't be enough exchange of gas between the water and the air for your fish to continue to live. So you always have to either pump some water, blow some water, blow some air on it to the point where you have some ripples on the surface of your fish tank, so that you get enough gas exchange so that your fish can continue to live. Happens right there in the fish tank, so just the same way it happens on the surface of the ocean. You create, a wave, ripples and motion of the water on the surface of the water, and thereby it allows the gas molecules in the water to exchange with those that are in the air. And it's a constant thing going on. There's, oxygen goes in and then oxygen comes out. Carbon dioxide goes in and carbon dioxide comes out. Nitrogen goes in, nitrogen comes out. So these things are constant, in and out, in and out, in and out, to the point where, that top level of water. Now, again, here's the thing. So all this is happening at the surface. So you got to remember that, the deeper you go, the less oxygen and gas that are going to be down there, just because they're far away from where the gas is getting it, in and out of the water. So that's why we're upwellings are kind of important, because that water moves away, that's been oxygenated, and it cycles back down when it reaches a cooler spot, and then that cold water comes up, has all the nutrients in it, and then gets oxygenated because it's now on the surface. So that's the way that those upwellings end up being so productive. So now these gas molecules dissolve into the body of the water. At the same time, other gas molecules that were already dissolved escape back in the atmosphere. This is an incredibly important exchange that takes place constantly on the surfaces of the bodies of water. The higher the air pressure, the more gas is dissolved in the liquid. The fish need oxygen to be in the water. The plants such as phytoplankton, need CO2 to be in the water. The ocean is a very complicated system of exchanges going on continuously between the organisms living there and also between the water and the atmosphere. So, there are a number of factors that play into how much gas can be dissolved into a body of water. Cold water holds more gas than warm water. So when you have that cold soda and you open it, it fizzes a little. But if you open a warm soda, boy, that gas wants to get out of that liquid very, very quickly. You'll end up fizzing it, and fizzes and overflows a lot more readily. Water deep under water with low salinity. Low salinity. Salinity means what? Salt. Can hold more gas. Think estuaries. So in those places where in an estuary where that fresh water and that salt water meet, that lower salinity water can hold more dissolved gases. There again, there's another reason that estuaries are such productive places along with upwellings, because that lower salinity allows them to have more gas dissolved in the water. Water deep under the ocean is under tremendous hydrostatic pressure. Remember, hydrostatic pressure is the water version of atmospheric pressure. But since water weighs 8 pounds per gallon, the pressure that exists deep under the oceans are incredible. That's why you can go up in in something that's in an airplane up where there's low air pressure, and the skin of an airplane is that thick. You go in a submarine, go down deep in the water, the metal that the submarine's made of is like that thick, because the hydrostatic pressure, water, there's so much more when you go down underneath the ocean versus going up. The deeper you go, the more pressure the water is at that level is under. The deeper you go, the more gases that can be held dissolved in the water. So here's the thing, so that water can hold more gas down there in the deep, but yet since it's far away from where the gases are getting into and out of it, there has to be some sort of exchange of waters, just like with the upwelling, to get dissolved gases down into the deep. So it's it's where we're going to run it. The currents and the upwellings and the downwellings become so important to sea life, by not only moving nutrients up, but moving oxygenated water down. So carbon dioxide is one of the most important dissolved gases in the ocean. If the ocean didn't absorb carbon dioxide and store it in dissolved form, life as we know it would not exist. The dissolved carbon dioxide, remember, carbon dioxide is what we breathe out. Carbon dioxide is what they say a lot of things, that we're talking about are bad for the atmosphere and causes the greenhouse, gas effect, carbon dioxide. It's important for plant photosynthesis, but it has many other important jobs as well. A lot of that carbon dioxide that's in the ocean reacts with the seawater and other things in it to form new compounds. Some of these are carbonic acid or bicarbonates. These new molecules remove the carbon dioxide from the water and lock it up into other forms. We talk about locking it up. That's the thing where we take it literally. It's like locking it into a cell. So we take this carbon dioxide that we really don't want in the atmosphere, because again, we're finding out it has more and more effects we're not happy with here living on the Earth, and being able to lock it up into a form that where it's not going to go back into the atmosphere. Yeah, that's pretty good for us. So the organisms that are in the ocean use these new molecules, the carbonic acid, the bicarbonate, in their life process. For example, many organisms in the ocean form shells. You guys have been to the beach, you've seen seashells. Those shells are made from carbon dioxide initially being, bicarbonates being used by these animals to build their shells. So from the shells we found on the beach to the delicate coral reef structures that are homes to a multitude of marine animals, organisms use the products of the carbon dioxide reactions to build their bodies and their homes. When these organisms die, that carbon dioxide is locked up in those, hardened dead shells and dead bodies of those structures of those coral reefs and stuff, and they remain in the ocean even after the animal that made them has died. We use the term locked up means that carbon dioxide that was once a gas in the atmosphere is now a solid form, is not going to return to a gas for a significant long period of time. So, fairly short lesson today, but again, I can explain how seawater contains dissolved gases. Remember, air pressure pushes the molecules down into the surface of the water. The water is agitated by wind and waves. Those molecules enter the water and become dissolved. But at the same point, molecules are also leaving the water and becoming undissolved. So it's a continuous process. But that is how dissolved gases get into water. But again, without this process, life on the Earth, as we know it, would not exist, because there would be nothing living in the ocean except for whales and dolphins, and they would have anything to eat, so they wouldn't exist either. So anyway, dissolved gases in the oceans resulting from air pressure pressing those molecules into the water. Great. I hope you guys have a great rest of your day. Just remember to answer your do now questions for the day. Remember to sign off down in the comment section. Say, hey, I was here for your attendance, and like the video. Please like the video. I'm getting. You guys are like signing in, but you're not liking the video. I don't care if you actually don't. Just like it anyway. It's part of YouTube. Like the video, sign up for the channel, and have a fantastic rest of your day. We'll see you guys again tomorrow on another exciting adventure into 8th grade science.